Okay, good morning, gang. I'll give just a few minutes since it seems like we're still missing quite a few folks. But I will go ahead and outline what we're going to do for the day while we're waiting for folks to arrive. Here we go. This is, of course, so, whoa, shit, come on now. Come on, .cam. All right, there we go. So, today we're going to begin section 7.1 on integration by parts. This is sort of the beginning of the real meat of the class. Those first few sections are nice. They give us some geometric perspective. They can be helpful for thinking like a physicist. You know, thinking of little differential solids and all the geometry and stuff is great. But today we're going to start learning new analytic methods, which is really the first third of this class. So, integration by parts is an analytic method. It's a method for solving integrals. Close my door here really quick. My wife is in the other room doing the same thing I'm doing now. Integration by parts is a backwards product rule. That's it, right? So U sub, the method that we've been playing with in our integrals for the most part, you can think of as a backwards chain rule, right? That's really what it is. And integration by parts is a backwards product rule in the same sense that U sub is a backwards chain rule. I'm gonna show you the method, right? The formula, theorem, how to use it, and a handful of examples. Before I get into that though, I just want to point out that if you come to our class in Canvas and you click on modules, you'll see all this review material. This is all good stuff. You'll see these things that I posted for the revolutions, the solids of revolution, the stuff that we were doing last week, including these two new ones down here that I think I showed you. If you haven't checked these out, though, do check them out, especially if you're still working on or still stuck on some of those problems. But there's also this, right? There's a whole module here on stuff for integration by parts. The first element here, I'm going to be showing you this today. This is nothing special. Paul's online, well, I mean, it is special, but I'll show it to you today. The Paul's online notes page is great, as they always are. It's full of lots and lots of worked examples where you can reveal solutions step by step. It's wonderful. He also has good explanations in there. Patrick JMT, these are YouTube videos where dude solves problems. Dude solves lots of problems. I would recommend checking these out if you get stuck. I'm just reminding you that that stuff is there. So integration by parts, what is it? What do we do with it? Let's take a look. I think the only fair thing to do is show you the theorem. It's a brand new pen. It's starting to get on my nerves. Come on. All right, so the theorem, this is integration by parts. Hereafter, I will refer to it as IBP because I get tired of writing that much stuff. It says simply that the integral of u times dv is equal to u times v minus the integral of v times du. Or in the case of a definite integral, the integral from a to b of u times dv is equal to u times v evaluated from a to b minus the integral from a to b of v times du. And in both cases, u and v are functions. So there's one version of the formula for indefinite integrals. There's another version of the formula for definite integrals. Think of this as like f and this as like g prime. And it says the integral of f times g prime is equal to f times g minus the integral of g times f prime. Looks a lot like the product rule. In fact, when I prove this for you, I'm going to show you a few proofs, but the only one I'm going to write down here is the one that I think is easiest to play with. We begin by rearranging the formula. So I'll call this equation 1, I'll call this 2. Begin by rearranging 1 as u times v equals integral of u dv. I'm just adding this over, plus integral of v du. And then we differentiate. And since this is all written in the abstract, I'm going to use the prime notation. So if I differentiate on the left, I'll get u times v all primed. If I differentiate on the right, I'll get all of that stuff primed. But over here, what happens when I prime this? Well, remember that taking a derivative and taking an indefinite integral, those are opposites. They undo each other, right? Like the integral of x is x squared over 2, and the derivative of that is back to x. So the integral of u dv, all primed, is just u times dv. The integral of v times du, all primed, is just v times du. So this is u times dv plus v times du. And this is what you're used to seeing, right? The derivative of u times v is u times the derivative of v plus v times the derivative of u. That's the proof, which is a statement of the product rule. Which we know to be true. So that's the proof. This is all well and good, but it doesn't show you anything about how to use integration by parts. It's just to convince you that this is a true statement, that this formula works. So if this proof isn't exciting to you or you don't care, that's fine. But this is why it's true, and that matters. We should be able to trust that our formulas come from somewhere meaningful. And really, this comes from the product rule. Another way of saying it is if you start with the statement of the product rule and you integrate on both sides, you get the integration by parts formula. Okay. How do we use it though? Let's look at an example. So again, things that you must have clear in your notes, the statement of the theorem here. Gotta have this in there nice and clear. The proof is not terribly important for the purposes of this class because this is a skill building class, but if you're the sort of person that cares why you're doing the shit you're doing, then I would include the proof too. But make sure you have these formulas somewhere nice, big, and clear in your notes, because this is what everything in section 7.1 hinges on. There's a lot of stuff that we can't integrate yet. There are a lot of functions whose integrals we don't know how to calculate. In general, integrals are much, much harder than derivatives. A good first example here would be something like this. X times e to the x dx. We want to integrate. In order to apply the integration by parts formula, I have to label part of this as u and part of this as dv. So I'm going to think of the x piece here as u, and I'm going to think of everything else, e to the x dx, as dv. Usually the way we do this, we come off to the side and we build a little table. So u here is x, and dv here is going to be e to the x dx. In practice, I'll give you a rule for picking u, and then dv will be whatever's left over. Our formula involves u, dv, and also du and v. So I need to calculate du from u and v from dv. So I need to complete my little IBP table over here. If u is x, then du is just dx. And hopefully you see why I don't want you using the letter u in your substitutions, because I don't want you to confuse that with this. If dv is e to the x dx, then v is the integral of dv. The integral of e to the x dx, that's just e to the x. And we never write the plus c's when we're doing the integration by parts table. We save the plus c for the very end. So I interpret my integral as the integral of u times dv. I fill out this table, and then I write down the integration by parts formula. It says the integral of u times dv should be u times v minus the integral of v times du. What is u? U is x. What is v? V is e to the x. Minus the integral of v, which is e to the x again, and du is dx. So the output from IBP always has an integral in it, but this integral should be easier than the integral you started with. Is this integral easier than the integral I started with? Well, yeah, the x is gone. I didn't know how to integrate x times e to the x, but I do know how to integrate e to the x on its own. This is x e to the x minus, well, what is this integral? That's e to the x plus c. And you're done. That's it. So we know you can't integrate products nicely, right? Like the integral of f times g is not the integral of f times the integral of g. That shit never works. Just like it doesn't work with differentiation, right? When you want to differentiate a product, f times g, you can't call that f prime times g prime. You have to follow the product rule. Here, this is the integral version of the product rule. We can always check our work by differentiating. If I take this x e to the x minus e to the x plus c, and I prime the whole thing, the c will differentiate to 0. That's x e to the x primed minus e to the x primed plus 0. I can split that derivative up over addition and subtraction, that's fine. And then when it comes to this piece, I would need to differentiate using the product rule. So I'll differentiate the x, leave e to the x alone. Add that to what I get when I leave the x alone, but differentiate e to the x. And then minus the derivative of e to the x is just e to the x. So we get e to the x plus x e to the x minus e to the x. These guys cancel. And you do just get x e to the x. So this really is the antiderivative of this. Okay. So at least for this example, integration by parts works. And if you really trust that proof that I showed you, then you should believe that it always works. It does. And it'll never lead you anywhere untrue. But the challenge in integration by parts is how you pick u and dv. Right? There was an element of choice here. I chose to split my integral up as this times this. Nobody told me to do that. That was my choice to make. And every integration by parts problem you do, you will have to make a choice like that. If you make that choice poorly, then the problem will not go well. The integral you get here might be worse than the integral you started with. But if you make that choice wisely, and I will give you a rule for how to make that choice wisely, then it will go well. And you can always check your work by differentiating. Questions on this example? Yes, Pablo, yes. Yep, that's the recipe. The recipe is that the integral of u times dv is always equal to u times v minus the integral of v times du. So the products there always go this times this minus the integral of this times this. So let me outline the procedure. First, you have to partition your integrand. The integrand is the thing you're integrating, right? It's the function in the integral. You have to partition your integrand into two pieces. One we call u, the other we call dv. And I'll give you a rule for this. You'll do this according to the Lipet rule, at least most of the time. I'll explain what the Lipet rule is in just a second. Then you fill out your IBP table. That's the thing that you saw in that last problem where I had u times u, dv, du, and v, right? That little table, and plug into the formula. That's these things. These are the IBP formula. Then finally, you look at the resulting integral. And solve however you can. Maybe that the integral that comes out here, right? The integral that you get at the end of your formula, this might require another run of integration by parts, or maybe some u sub, or maybe it's an easy integral. Maybe it doesn't require any of those things. But in any case, you'll have your original integral is equal to a bunch of shit like this, There will always be another integral in that stuff, and you have to figure out what to do with this guy. All right, this is our basic procedure for running IBP. My cat's gonna tear down the door unless I let him in, so I'm gonna do that while you guys are writing. You cat, it's rude, it's rude. What you doing, big guy? So that LIPET rule, really what the LIPET rule is it's a guideline to help you pick U, and then you always choose dV to be everything else. So you'll choose U according to a hierarchy, and I'm going to misspell this word, hierarchy, then let dV be everything else. The hierarchy looks like this. L stands for logs. Are there any logs in your integrand? If so, you should choose that to be U and let everything else be dV. If there are not any logs, then you look, are there any inverse functions? Like arctan or the inverse sine function. If there are not any logs and there are not any inverse functions, then you should look for any polynomials. If there are any polynomials, then you will pick those to be U. And then if there are none of those, you look for exponentials. If there are none of those, you look for any trig. So it goes like this. And this is your hierarchy for picking U. If there are any logs, any log functions, pick that for U. Pick that to be U and let dV be everything else. If there aren't any logs, look for inverse functions. If there are any inverse functions, let that be U, or pick that to be U, and let dV be everything else. And so on. So you come down this list until you find something that's in your integral. Once you find something coming down this list that's in your integral, you'll pick that to be U, and you'll let dV be everything else. Then you apply the formula. That's how this rule works. And that's it. This is your total strategy for integration by parts. So I know there's a lot written here. I think the easiest way to get a feel for and a hang of this is with some examples. But if there are anything specific here that you're curious about, you can't read, you want to know what I wrote or what it is, now's a good time to ask. So the third step here says, look at the resulting integral and solve that however you can. So first you split up your integral into u and dv. We're actually forming a partition, which means that two separate pieces don't overlap, come together to form the whole thing. Partition your integral into u and dv. Then you fill out the IBP table and plug into the formula. The very last part of that formula is another integral. So you look at that integral and solve that however the hell you can. Okay. And then the way we choose u and dv is according to this LIPET rule. If you come down this list in order, looking for these things, if you have any logs, then you should let u be the log function and let dv be everything else. If there are not any log functions, then you start looking for inverse functions. If there are any inverse functions, you let u be the inverse function and let dv be everything else. If there aren't any inverse functions, then you look for polynomials. If there's a polynomial in there, then you should let u be the polynomial piece and let dv be everything else. That's what we did for the x e to the x. We didn't have any logs, didn't have any inverses, but we did have a polynomial. X is a polynomial. So I let u be x and I let dv be everything else, e to the x dx. That's the way this works. So let's take a look. Let's look at a few more problems. Here I want to integrate x times the inverse tangent of x. Definitely not a problem I know how to solve already. Definitely not a u sub thing.
Would you
Looks
use
like this sort of, I'm sorry, go ahead.
Would you use the inverse tan function as your u and then let du be everything else?
So we'll follow the LIPET rule, right? So I don't have any logarithms. So then I look down to the next thing. The next thing is inverse. I do have an inverse function, yeah. So I'm going to use IBP here. And u is going to be my no logs. So I come down and I look for inverses. I do have an inverse function, so I'll let u be the inverse tangent function, just like she's saying. And then dv has to be everything else. So what is everything else here? It's x times dx. Then du, I need to fill out my integration by parts table, is 1 over 1 plus x squared dx. And v, if I integrate on both sides here, I'll get 1/2 x squared. Interesting. So this is my IBP table. I like to put it in a little box, just like we do for our substitutions, and then we write down the formula. U times v minus the integral of v times du. So that's the inverse tangent of x times 1/2 x squared minus the integral of 1/2 x squared times du. I can pop the 1/2, so now I look at the resulting integral and I solve it however I can. This is the same as x squared over 1 plus x squared dx. Does anybody know how to solve this integral? So this is the result from IBP. U times v minus the integral of v times du. Here's the v, here's the du. And I popped the 1/2 out, and I took this x squared and I put it upstairs here. So now we need to look at this integral and see, have things gotten better or worse? Do I know what to do with this? The answer here is yes, things have gotten better.
Wouldn't the x squares just cancel out?
They don't cancel. You can't cancel unless you can factor. X squared is not a factor of the bottom because you've got the 1 here. Remember, the only time you can cancel is if you've got a shared factor top to bottom. So the step immediately before canceling needs to be factoring. You cannot factor an x squared from the bottom. But there is something else we can do. Did anybody go through the review material in the modules?
Could you split up the top and the bottom? So have x squared times 1 over 1 plus x squared and then raise that to the -1 power?
I'm not sure I follow. There is some algebra we can do here, but it's not so much splitting up over the bottom. It's long division. You can divide the top by the bottom. You can long divide. There's a cheap way to do this. I call this poor man's long division. We agree that this is the same as this. I added 1 and I subtracted 1. So I didn't change the top. But now that I can split up, that's 1 plus x squared over 1 plus x squared minus 1 over 1 plus x squared. Or another way to say that is, now you can cancel these, right? Because this is a shared factor top to bottom. So that's 1 minus 1 over 1 plus x squared. So this is some algebra side work. And what it tells me is that my integral here is inverse tangent of x times 1/2 x squared plus 1/2 integral 1 minus 1 over 1 plus x squared dx. This can be rewritten as this. It's a sneaky algebra trick. We'll talk more about this sort of algebra. What's really going on here is long division. We'll talk more about that when we get to the section 7.4 on integrating rational functions. But it is something that we should have seen in the past. If you haven't seen it, that's okay. We're just dividing these polynomials. I'm dividing x squared by 1 plus x squared. And the result is 1 minus 1 over 1 plus x squared.
Isn't it minus 1/2 for the, like, before the integral?
Yeah, thank you. Thank you. Transcription error there. That this is a minus. Okay, now I do know how to do this integral. So this is arctan x times 1/2 x squared minus 1/2 times the integral of 1 dx is x. The integral of 1 over 1 plus x squared, what is that?
Inverse tangent of x.
Yeah, he's just inverse tangent x. And at this stage where I have no more integrals, I should slap on my plus c. So if I collect all my like terms, I'll distribute the 1/2 maybe, put everything together here. So this is 1/2 x squared times inverse tangent of x minus 1/2 x, and then minus makes plus 1/2 inverse tangent of x plus c. Good stuff, right? You could combine this term with this term if you wanted to, but you don't have to. Let's take a look at another example. I'll give just a second here. While you're finishing this up, you can start thinking about one that we've also not done before, just integrating good old-fashioned natural log of x. If I want to integrate the natural log of x, again, you can think about it for a little bit, but no u sub will work. It's definitely not something we have an antiderivative for. I know the derivative of ln x is 1 over x, but I don't know what the integral of ln x is. So I can try some IBP. That means I need to choose u and dv, and I'm going to choose them according to that Lipet rule. There is a log function here. So according to that Lipet rule, I should choose ln x to be u and everything else to be dv. Well, everything else is just dx. Now I finish filling out my IBP table. Du is 1 over x dx, and v is the integral of dv, that's just x. So according to my IBP formula, the integral of u times dv should be u times v, that's ln x times x, minus the integral of v times du, that's x times 1 over x dx. And here, these do cancel, right? X times 1 over x, that's just 1. So this is the natural log of x times x minus the integral of 1 dx. And the integral of 1 dx, or just the integral of dx, is x. So this is, I'll write the x out front because it looks better that way. That's x times ln x minus the integral of 1 dx is minus x, and then we slap on our plus c. So before we didn't know how to integrate the natural log. This is the integral of the natural log. And it comes from IBP. So hopefully you're starting to get a feel for the kind of world of things that this opens up. Integration by parts opens up a huge, huge, huge mass of things. It might be the most important integration technique we learn all semester, right? You guys are supposed to know U sub already, but between this and U sub, this is definitely more important. We use this all over the place, even in research applications.
So would you say to do U sub as your primary go-to, or IBP?
It depends. So like, you know, is the chain rule or the product rule like more useful for differentiating? We use them both, right? There are some things that you use the chain rule on, there's some things you use the product rule on. Same sort of thing here, right? Think of this as your backwards product rule and U sub is your backwards chain rule. So they just apply to different families of functions. It's hard to say which family is larger. Probably the IBP family is a little bit larger, but it totally depends. So usually what I'll do is when I look at an integral, I'll ask, can I do this with a substitution? Substitution a little bit easier, a little bit faster usually. If you can do it with a substitution, by all means, do that. But if you can't, then you should start thinking about IBP.
Okay, thank you.
So we looked at x e to the x, we looked at x arctan x, we looked at the natural log of x. Kind of along the same lines as the x e to the x integral. We don't know it yet, but e to the x and sine x and cosine x are related to each other in really, really intimate ways. So anytime you have like a polynomial times e to the x, sine x, or cos x, you'll do the same sort of thing. We're going to run IBP. And according to our LIPET rule, we'll pick u to be the polynomial piece, right? No logs, no inverse functions. But there is a polynomial. T squared is a polynomial. So I'll pick u to be t squared and dv to be everything else. That's cos t dt.
Wait, but how is it a polynomial if it only has one term?
Definitely still a polynomial, still made up of monomials, because the power here is a positive whole number. That's really all we need. So t squared plus 1, t squared minus 5t plus 7, all of those would be polynomials. It's just a polynomial with one term. So du here would be 2t dt, and v would be the integral of cos t, that's sine t. So a polynomial doesn't have to have multiple terms, it just has to satisfy that definition. Has to be made up of whole positive powers of your variable with constants added up. So here there's only one term, but it does have a whole positive power. So this is a polynomial. So if I pick u to be the polynomial piece and dv to be everything else, then I complete my IBP table by finding du and v. It looks like this. And now I will plug all of this information into my IBP formula. And it says that that integral, the integral of t squared times cos t dt, should be u times v. That's t squared times the sine of t minus the integral of v times du. I'll write that as 2t times the sine of t dt. I just like to put the polynomial piece out front. Looks prettier. So everybody see how this is the output from this IBP table? Now what I started with was a polynomial times a trig function. And the integral I got is a polynomial times a trig function. Have things gotten better? Is this integral in any way easier than this integral? What do you notice?
Could we just take the constant out of the integral too?
You can. We can pop the 2 out. That's a good move. Let's do that. So I have t squared sine t minus 2 times the integral of t times sine t dt. So what do you notice? What has changed here? Compare this integral to the original integral. What has changed?
The power?
Yeah, the degree of the polynomial went down by 1. So if I do this shit again, this guy will go away. And I'll just have the integral of maybe sine or cosine. So we need to run integration by parts again on this. Again, following my LIPET rule, I'll pick u to be the polynomial piece and dv to be everything else. Then I'll complete my table. Du is just dt. V here would be the integral of sine t, that's negative cos t. And then I replace just this piece by his IBP formula. So the t squared sine t out front stays Then I'll have minus 2 times, and I'll open a big parentheses. And then what goes in these parentheses is the IVP stuff from this table. U times V, that's going to be negative T cos T minus the integral of V times du. That's minus the integral of negative cos T dt. And you see how careful I'm being with my parens, right? Because there's all these negative signs stacking up that you'll need to be very, very careful with. We can simplify a little bit. The 2 minuses here will make plus integral cos T dt. But then when we distribute our negative 2, we'll get T squared sine of T minus minus here makes plus 2T cos T, and then minus plus here makes minus 2 integral cos T dt. And the magic is no more polynomial. You've differentiated the polynomial away. You just have the integral of cos T. Oh, well, that's sine T. So this is T squared sine T plus 2T cos T minus 2 times the integral of cos T. That's 2 times sine T. And then we slap on our plus C because we're done. So take a second, pay extra careful attention to like these 3 steps here. When we used integration by parts for the second time on this integral, I put the whole expression that comes out in parentheses. That's very important because this 2, this minus 2 was meant to multiply this whole integral. And this whole integral is this whole expression. So without these big parens, I'm fucked. And then within those parens, we have a negative from the IBP formula. We have a negative coming from the antiderivative of sine. And you have a negative here, again, coming from the antiderivative of sine and that formula. So you get all these negatives, and you got to be careful with them. Clean up inside the parentheses a little bit, anything that is obvious, like this minus minus here, making a plus, and then distribute whatever is out in front. If you do it this way, you'll be good. Right? But if you're sloppy about this, it'll be a mess. You'll spend hours trying to chase down some little mistake, and it's going to turn out to be a minus sign somewhere. It'll be frustrating. So be very, very organized with your work, right? I've tried to say that in the first 2 weeks here, and this is one of these places where organization matters a lot. Questions on this guy? How am I doing for time? Doing good. I'm doing good. Okay. I think if there are any classics here that I've left off. We did x e to the x. We did order 2 times transcendental. Did 2 straight inverse functions. Okay. So I want to take a second to show you another interpretation. Last call for questions on this. We haven't done a definite in it. Yeah, I'm going to do a definite integral. So yeah, let's do one more example here. I'll do a definite integral, and then we're going to look at at a picture proof for integration by parts, and then I'll let you guys go. Okay, let's do sine inverse. So first note, this is a definite integral, right? Has bounds. So we're going to use the formula for definite integrals. It's a little bit different, remember. And then the thing we're integrating is sine inverse. This is not something I have a formula for from Calc 1. It's not a basic antiderivative. It's also not something I can do just by making a little u sub. So I know I have to use IBP, or at least I should try IBP. And according to the Lipet rule, I should pick u. Well, I don't have any logarithms. I do have an inverse function though, so I should pick u to be my inverse function and dv to be everything else. Everything else here is just dx. Du, the derivative of the inverse sine function, is 1 over the square root of 1 minus x squared. So that times dx is du. And v, if we integrate, v is just x. So according to my IBP formula for definite integrals, the integral of u times dv is u times v. Evaluated between bounds, and people forget this all the time. Do not forget the bounds here. Minus the integral, again between bounds, of v times du. So this is the output from this IVP table for this integral. Got to know those inverse trig derivatives. Those are important. They're going to show up again and again. And here we're going to need to know some facts about the inverse sine function in order to do the evaluation. You should always do the evaluation right away. Don't wait. So this will be the sine inverse of 1 times 1 minus the sine inverse of 0 times 0. And here, this I can rewrite as the integral from 0 to 1 of x over the square root of 1 minus x squared. Okay, help me out, guys. What is the inverse sine of 0?
Pi over 2.
For what angle between negative pi over 2 and pi over 2 is the sine of that angle equal to 0?
0.
Yeah. For what angle between negative pi over 2 and pi over 2 is the sine of that angle equal to 1?
90.
90 degrees, and in radians, that is
Pi over 2.
pi over 2. Yeah. So we always use radians. Always, always, always use radians. If you insist on writing something down with degrees, make sure you use the degree symbol at least. But please, 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 this is a math class. We use radians. So this is pi over 2 minus 0. That's pi over 2. How much nicer is it to just write this than all this shit? Don't keep copying down all this shit from line to line. It'll give you a headache. Just do the evaluation and it's done. So this is pi over 2 minus the integral from 0 to 1 x over the square root of 1 minus x squared. How do I do that integral? I still need to do this. How do I do this?
Could you do IBP again?
We could, that's an option, but it might not be the best option. This guy doesn't require IBP. There might be an easier way. There is an easier way.
You said
U sub. Yeah, now here I don't want to use the letter U in my substitution because I don't want to confuse myself with this. So I'm going to use the letter Z. What do we substitute for?
1 plus x squared.
Or 1 minus x squared, right? The thing under the square root. So then dz is minus 2x dx. Also, I need to change my bounds. When x is equal to 0, z is equal to 1 minus 0 squared. That's 1. And when x is equal to 1, z is equal to 1 minus 1 squared. That's 0. So the bounds are going to flip over. What do I have in here for my differential? Well, this is negative 2x dx. I have x dx right here. So this piece is negative 1/2 dz. I'll write it out. This is pi over 2 minus integral. I'm going to keep it in terms of the x's for now. 1 over 1 minus x squared under the square root, just to help us see how the substitution is going to go in. All right, so I'm thinking of it like this. The x dx is negative 1/2 dz. And this piece will be 1 over the square root of z. So this is pi over 2 minus integral. Now I'm going to put everything in. My old lower bound is 0. My new lower bound is 1. My old upper bound is 1. My new upper bound is 0. 1 over the square root of 1 minus x squared is 1 over the square root of z. And x dx is negative 1/2 dz. There's the substitution done. I can bring this out front. It'll make this positive. One over the square root of z is z to the negative 1/2. And then finally, our antiderivative step for that guy. If we add 1 to that power, negative 1/2 plus 1 is positive 1/2. So that will be z to the positive 1/2 divided by positive 1/2. That's the same as multiplying by 2. And we evaluate between the bounds. We'll continue up here. We've got the pi over 2 plus 1/2 times 2 times 0 to the 1/2 minus 2 times 1 to the 1/2. That's the square root of 0. That's 0. And that's the square root of 1. That's 1. So this is pi over 2 plus 1/2 times negative 2, 0 minus 2. So that's pi over 2 minus 1. Excuse me, sorry. Sleepy this morning. So here we did some IBP, and then the integral that popped out required U sub, or required a substitution. We did the substitution slowly, right? Like all three of these steps really could be combined into one. We could go straight to here. But I'm trying to help everybody see exactly where everything is coming from. I'm hoping that we're getting good at this shit. This shit should start coming fast. In particular, the stuff with the differential. So shuffling this over here and then rewriting it like this, I'd like us to be able to get to this step a little bit quicker. So in the future, I won't go through the substitutions quite as slowly. But the integration by parts, this is what we're working on learning now. So questions on the IBP step or really anywhere within this problem? Anything you would like to look at? Again, some tricks for doing these definite integrals by parts. Don't forget the bounds. Bounds are super important, and they go to everything, not just the integral. They also go to the u times v piece. And you want to go ahead and do this evaluation right away. Because look, everywhere I wrote pi over 2 here, I would have to write this whole bracket statement unless I went ahead and evaluated early. I don't want to write that 1,000,005 times. And it's a pain in the ass enough just to write the pi over 2. I don't have to write all this. So go ahead and do the evaluation step right away, as soon as you can. And then deal with what's left over however you must. We've seen sometimes that means another run of IBP. Sometimes that means some substitution. And as we learn more and more techniques, we'll see that sometimes that'll mean something else entirely here. Last call for questions on this guy.
At the bottom, where'd you get the 2 from?
So I'm integrating z to the negative 1/2. So I'll add 1 to that power and then divide by that new power. If I add 1 to negative 1/2, I get positive 1/2. So I'll have z to the positive 1/2 divided by positive 1/2. Dividing by positive 1/2 is the same as multiplying by 2. So the step here where you'd write this as z to the 1/2 over 1/2 and then flip and multiply, I did the flip and multiply already. Is that making sense?
Yeah.
Okay, cool. All right, so before I let you go, a little thing here. We're not going to solve this integral today. I just want to show it to you. This problem is famous. This is called the damped harmonic oscillator. You may have from your trig class learned about harmonic motion or harmonic oscillators. Sine and cosine are your typical harmonic oscillators. They are like oscillating waves, right? And they do so according to what's called they're called harmonic functions or simple harmonic motion. If you slap on a piece like this, remember what e to the negative x does, it wants to go down to 0. So this piece is taking your cosine wave and like smushing it down over time. Let me show you. Here's your regular cos wave. Here's e to the negative x cos x. Okay, I don't care about what's happening on the left, I care about what's happening on the right. So what this e to the negative x piece does is it takes your cosine wave and it smushes it onto the x-axis. Here it's really doing it quite quickly. So maybe if I wanted to, I could make this like like this to help you see it. All right, you see the cosine wave here getting smushed down. Think of this like a pendulum with a dash pot. Something like this. So where do you see this sort of behavior? If you had a pendulum hanging from a ceiling, swinging back and forth, so it's got some mass here. And you put, do you know what a dash pot is? It's that thing on a door that keeps you from slamming it. It kind of goes if you try to close the door too fast. You see them at like, you see them on campus at Santa Fe or any like large industrial facility or convenience stores, places like that where you have a door that gets used a lot. If you were to take a dash pot like that and attach it to something like this, then the pendulum will still want to keep swinging, but it's going to swing less and less each time. If you want to figure out how many times the pendulum swings back and forth or how much distance that any sort of damped harmonic oscillator will travel, you'll have to do an integral like this. And these are also done by parts. This will require integration by parts, but it's a harder problem than any of the ones we've looked at today. So we're going to save this guy for for Friday. Right, this and a few others are called looping integrals. Essentially what you'll do here is you'll run integration by parts some number of times until your original integral shows back up. It's pretty cool. And then you'll solve an algebraic equation for your integral. Honestly, it kind of feels like magic. You're like, I never actually solved the integral. I just like did IBP and I got this equation, and now somehow I'm able to like solve that equation for the integral rather than finding an antiderivative directly. But it works. So here's what I would encourage you guys to do between now and Friday. Come to our class in Canvas, come down to the module on integration by parts. There's a picture proof here, gives you another way of thinking about what's going on in integration by parts, a way of thinking of this as areas. And you should check these out. This is pretty good. It's not super hard to understand. Although I think the easiest way to get what IBP is the proof that I showed you using the product rule. And there's discussion of that down here also. But you can interpret this in terms of areas. Then I would look at some of these other things. So if you're having a hard time with IBP, take a look at these Patrick JMT videos. The first 3 Patrick JMT videos here are problems just like the ones we've done in class. They're not especially hard, and they'll help you get a feel just by doing more examples. But then this last guy down here, this is a looping integral like the ones that we're looking at. You've got e to the 2x times sine x instead of e to the negative x times cos x. All of those sort of integrals where you have an exponential times sine or cosine, as well as a few other integrals that I'll show you soon, are looping integrals. And they will require integration by parts, but you'll have to think about it a little bit differently. So in a few minutes here after our class ends, I will get your second homework, or I'll get your third homework up. That'll be the homework on section 7.1. If you have not finished the second homework, please go ahead and submit an extension request. I've been going in and clearing those out. I cleared them a few times over the weekend, but I'll clear them again today. I'd like you to knock that out. I'd like homework 2 to be completely done today. If that's totally impossible, I understand, but again, please try. It's very important that we don't fall behind. Integration by parts is the start of us learning new analytic methods, and that's going to be the bulk of what we'll do between now and exam 1. That'll also be the bulk of the content on exam 1. As much as this volume stuff is fun, really the skills we need you to be picking up in Calc 2 is this sort of shit. So focus hard on homework 3, 4, and 5 before the exam. Make sure you get caught up so you can be focusing on those. And if you have any problems, don't hesitate to reach out for help. I will be here to help you, but make sure you're working hard on this. Check out some of these examples. I think they will help you. And then another thing you could be doing to kind of get yourself ready for what's coming is reviewing trig identities, because you see where we're going next, right? Our next section, section 7.2, is all on integrals of trig functions. And it should come as no surprise that in order to integrate trig functions, we will need trig identities. We'll be using them quite a bit. So I would strongly encourage you to prep for that. That is really all I have for you guys today. Do you guys have questions for me on any of these examples or anything that we've looked at here?
I just had a question about the division one again. I was struggling to understand that.
So, let's see. Let's see. I think I might have moved that one over here. Yeah. So going
yeah.
to here. The thing that we're doing there is polynomial long division. And if you take a look at here, this guy, there's a few videos and links I have for polynomial division. The way I did it here is kind of a shortcut where you add and subtract 1. So I took my numerator, which was x squared, and I realized that it's off from my denominator only by this plus 1. So okay, I want to introduce that plus 1. That means I also have to subtract it because I need these things to be equal to each other. So x squared is the same as 1 plus x squared minus 1. And then I regrouped. I took this over this minus this over this. And then these guys cancel, and I just get 1. 1 plus x squared over 1 plus x squared, it's like 5 over 5. That's 1. And then this piece is just minus 1 over 1 plus x squared. We could do this out the long way. If you wanted practice with long division, that is certainly doable. I don't have a blank side. I know one of these does. Yeah, here. So another way to do that is to take the polynomial x squared and say, all right, I'm going to divide that by x squared plus 1. We think of x squared as x squared plus 0x plus 0. And then I just pay attention to the lead terms. I ask, what do I need to multiply this by in order to get this? Well, that's a 1. And then I go ahead and distribute that 1 here. So I'll get x squared plus 0x plus 1. And then I subtract the rows. X squared minus x squared, that's 0. 0 minus 0, that's 0. 0 minus 1, that's minus 1. So what this says is that x squared divided by x squared plus 1 is equal to this plus this over this. This is my remainder. So this would be plus negative 1 over 1 plus x squared, which is what we got before. Or you could write it as, sorry, the x squared plus 1, 1 plus x squared, same thing. So this is how you do that division out the long way. And then, you want to integrate this. That's the same as integrating this. Which is what we did, right? But that shortcut for long division is a nice shortcut. The add and subtract trick that I used there is a useful trick. But if all of that stuff is like foreign, it's been a long time, or your pre-calculus class didn't spend enough time dividing polynomials, God knows I've seen way too much of that, especially here at Santa Fe, where that gets skipped. That's why I have these resources in here for you. So take a look at these. Each of these will walk you through several polynomial division problems. And it's useful here. It's useful in what we're doing now. You'll bump into it from time to time. And it's absolutely critical when we get to section 7.4, where we'll be doing a lot of that stuff. Okay. So this is where I have to end it for today. Please, again, if you have not finished homework 2, go ahead and submit an extension request right now. I will go in and pop those. Watch for homework 3. I'll be opening that in the next few minutes. And try to keep up with this stuff. If you have any hard problems, any difficulty with the integration by parts homework or the other previous homeworks, you can come see me in office hours, or you can send me a message on Canvas. Either one of those is a great way to get some help on a problem. Otherwise, I will see you guys on Friday when we will attack some looping integrals by parts. And then that will be the end of our week. So I hope you guys take good care of yourselves. And if you would like help with anything, don't hesitate to reach out. I do see that Sergio sent a message here about putting together a group me. I think that's a great idea. I won't interfere with any of that. Just want to remind you guys to be ethical. Whatever you do in those outside things, make sure that what you're sharing is helpful for everybody, and that you're not stifling anybody's learning process. But I do think it's a good idea. Contact each other, talk about shit. And if you have any questions for me, you know how to get a hold of me, okay? Take care, guys.